Good afternoon and welcome to this webinar. My name is Marco De Biasio. I'm product manager at SCIA, and today we are going to discuss in this webinar about seismic analysis in SCIA Engineer version 24. The topics that we are going to see today are this one. First of all, we will see the model analysis, what it is and how it works. Secondly, we will see how to set up a model with the reduced model IRS for model analysis. Then we will have a look at how to efficiently use property modifiers in seismic analysis. Then we will go to look at the seismic analysis through the method of response spectrum. And finally, we will have a look at the story results and the use of integration member for seismic analysis. So let's start with the first topic, that is the model analysis. What is model analysis? Model analysis is a kind of dynamic analysis that serves the scope of finding the natural vibration modes of a structure. So how the structure will vibrate under a dynamic solicitation that can be of seismic nature, but also of other nature, like it can be excitation due to people working on a footbridges or excitation due to a rotating machine and so on. Model analysis so is able to extract the way in which the structure will vibrate when excited by dynamic load and also the frequency of excitation. To see how this is implemented in SCIA, let's move directly to the software where I prepare a model for illustrating. This is the model I prepared. It's a reinforced concrete building, multi-story. As you can see, there are 5 stories, 1, 2, 3, 4, 5 above the ground, and 2 are under the ground. There are parts that are of masonry, the one that I put here in red, and for the rest, all what is gray and also this green here are parts of reinforced concrete. Let me switch the visualization in isometric, it's more clear. So if I want to perform model analysis on this model, what should I do? Of course, I should enable the features into the project settings. And once that is done, first thing that I have to give is an input concerning the masses of the structure, because I remind you what changes between a static and a dynamic analysis is that in the equation of the equilibrium for dynamic analysis, the terms that multiply the mass for the acceleration is present. In order to assign the masses, I go on the part of relative to loads, where I find 2 items, mass groups and combination of mass groups. With mass groups, I can give, as the command suggests, different kind of mass groups. For instance, by default, the one attached to the self-weight is already created. What means it means that all the self-weight of the mass of the structure is automatically translated in mass. It is linked by default also to the load case. It means if I change something in the structure, the masses are automatically updated. If I want to create other mass group, simply I do new, and I can select with respect to which load case I want to link these mass groups. For instance, I want to do a mass group linked to all the dead load that is applied, and another linked to all the live load that is applied on this building. It's always useful to select this checkbox in order to keep the masses updated with loads. So if I do a modification into the applied loads, the masses automatically update. I could also create, if I want, another mass group that is not bounded to a load case. In such a case, I switch to no. You see, there is not anymore the possibility to link to a to a load case, and in that case I will have the possibility to input masses into the model. For instance, I can put manually masses in nodes, on 1D elements, on edges, on surface, and so on. It's the same way as it is for the load cases. I can find the masses here, so the group of masses that I defined, and if I go on MG4, the group of mass that I defined manually, let's say, I can input into this MG4 additional masses by the hands. I will not do for the purpose of the exercise, but you can know that it is an option that is available. So now that we created the mass groups, let's go to combination of mass groups. Here I can say, I can specify for the analysis that I want to perform which mass groups I want to consider. Because it's true that I inserted several masses groups into this model, but I can choose to perform the analysis just with one if I want, even if I put several. In this case, I will select the 1, the 2, and the 3, the one meaningful that I entered, and I will do OK. Of course, there is possibility to act through a coefficient on the masses on each group in order to quickly scale the value of that mass. For instance, Eurocode suggests to modify the masses associated to variable load cases with a factor that depends on several parameters. I can do here, for instance, I put 0.3 for the masses associated to my variable load cases, but be careful, check before in the table of Eurocode to be sure which value you have to use in your particular study. So now that that is done, I just close, and if I go to compute the model, I have the option to compute the model analysis. As you can see, by default, the analysis is done for 10 modes. The software will go to look for 10 natural vibration modes, but I can change this parameter. Of course, I can change also the mesh settings, and it's always advised to do a finer mesh for dynamic analysis. For instance, to put at least 5 elements into the 1D members. And into the advanced solver setup, I can find some option in order to specify which kind of solver I want for the model analysis. The default one works very well, so no need to change. I can specify the number of eigenmodes that I want to compute. So if I want to compute 200 eigenmodes, I can put here simply 200. Now for aiming at speed, I will just put 10. Also, I can specify which kind of modal mass matrix I want to use, and if I want to use the reduced system. We will see this in a while into the webinar what is. So I will just keep the default value, and I will click on compute. Now the model will compute. For sure, first step is the mesh, and after the model analysis. As you can see, I have just one item because I selected to perform the model analysis only for one combination of mass. But if I would have defined more combination of mass group, it would have computed for more combination of mass group. So computation is done. Let's go to have a look at the results. Which results I can expect for this kind of analysis? As I said before, we have eigenmodes and eigenfrequencies. So the vibration mode, how the structure vibrates, and the associated frequency of this vibration. In order to see the vibration mode, I can simply go to results. For instance, go to the deformation and select the mass combination, and here I will have all the eigenmodes that I computed. So if I select the first one, and in order to go quickly, I select here a wireframe, I do refresh, and I will see the first vibration mode. I select the second, and I see the second, and so on. If I want, I can also see an animation of these results. In order to do so, just select the animation window that can be resized as you want, and click on play, and it will animate the results that are on the graph, on the 3D scene window. If I select, for instance, another, let's say this one, and I do the same animation window, it will animate this one. You see a pumping mode, the vertical one. So these for the modes of vibration that are always useful to look at in order to understand a bit how the structure will behave under excitation. And if I want to have a detail about the frequencies that are computed, that of course you can see here, you have 1.17 Hz for the first, 1.95 for the second, and so on. If you want to have a more detailed overview, you can go in Calculation Protocol and select Eigenfrequency, refresh, and here you will have a detail of the results of the modal analysis. So you have moving mass and total mass of the model, and the 10 eigenmodes that are computed, each one with its frequency and then the reciprocal, the period, and the participation factor for each one of these modes. As you can see in this table, that I will go to increase here in terms of dimension to be more clear. You see the first mode, the one associated to 1.70 Hz, mobilize almost 55% of the mass in direction Y. The second mode, the one at 1.95 Hz, mobilize 54% of the total mass in direction X, and so on. So here you can have the participation factor for each one, so for each one of the modes. And you can see also the cumulative sum here. So you can see that with 10 computed modes, I mobilize almost 56% of the mass in direction X, almost 70% of the mass in direction Y, and almost 86% in direction Z. The value here are for rotations. As you can see, with this analysis, considering only 10 modes, we don't reach a percentage of moving mass equal or superior to 90% as Eurocode asks for. So what we can do in order to do that? There are several options. First option, simpler one, is just asking for more modes till when we will reach the 90% in X and Y direction. And so with 10 we are already at 55 for X. Probably with 50 modes we will reach the 90%. Another option would be to use the IRS. What is the IRS? Let's go back to the PowerPoint in order to show that before to have a look at it directly in the software. So the IRS is a particular way of condensation of the numerical model that aim at reducing the number of degree of freedom of the initial model, so to have at the end, as a result, a model on which the analysis is computed that is much more light in terms of degree of freedom. And which is the advantage of this? Is that for sure there is an elimination of local modes, because as you know, less degree of freedom, it means that there are less vibration modes. Also, because of the elimination of local modes, there will be a better convergence to the modal mass, so to the 90%, the famous 90% of desired participating mass. And of course, because there are less degree of freedom, there will be also a reduction of calculation time. How to set up this model? Simply, one has to define the stories into the building. Then he has to enable the IRS. Just some word before to move to the software, how it works. It's really simple. We have at the beginning our 3D model. We set up the stories as it is shown in this picture. And then we set up the IRS. The model analysis will be performed on the IRS model, that at the end is just a simple stick model that is equivalent to the initial model. And finally, the results of this model analysis will be projected back on the initial mesh, so to have a full recuperation of the results without to not lose anything. And the example in the picture, it's really clear. You see at the beginning I had a mesh with 15,000 degree of freedom. At the end, for the same model, I have just 24 degree of freedom, 600 times smaller. And the results that I can obtain are really fully comparable to the one that I can obtain computing on the initial full model. But let's go back to the software in order to set up the IRS on the model of the sample. So I will open again SCIA, and the first thing that I have to do is to define the story. In that case, I already defined them, so you can see the story level are already in the model. But for the people that don't know, in order to set up story, just go to look for the command here, and you have the possibility to set up the different level that correspond to the different slab of your structure. It's really simple. Okay, then the only thing that is missing in order to enable IRS is simply go into the solver setting, advanced solver setting, and enable this checkbox, use IRS. That's all. And if I do that, I can just click on calculate. It will do the same calculation of before, so the same model analysis. Difference with respect to before is just that now it will use the reduced model instead of the full mesh. And if I go to look at the results like I did before, for instance, I can go to look at the deformation exactly in the way as I did before. I can find very comparable results, exactly the same as before. The vibration mode and so on. I have the same results also if I go to look for the animation. Again, this is a computation that has been done on a stick model, but my results are on my full mesh. And if I go to look at the calculation protocol for the eigenfrequency, I click on refresh. I have again that now I computed 10 modes, and the results are absolutely comparable to the one of before. Just the computation has been much quicker. Now, as you can see, even computing with the IRS, in this case, with 10 modes, I didn't arrive 90%. I see that the values are higher with respect to the one that I had before, and the mobilized mass is larger than before, but really of a marginal value. Where is this difference? This difference comes from the fact that here I have in this model two stories that are underground that are not really moving so much. Why not? It's because they are constrained by the surface support. It means all this mass that is here cannot move. So because it cannot move, we will not find it into the mobilized mass that is reflected by the calculation protocol. So what we can do in that case, that it's really a case that is very common in practice. What we can do is to apply a property modifier in order to remove all the mass that is underground that cannot move due to seismic excitation. In order to do that, just let's enable the property modifier into the project data of my model. I go to click to property modifiers, 2D property modifiers, and I create a modification group, okay, and into this modification group I say okay, I don't want to do any kind of modification of stiffness. I could do, of course, if I want. As you know, Eurocode advises to consider a cracked stiffness for analysis of reinforced concrete building, so I could just put a coefficient to take into account of the axial and bending reduced stiffness, but I will not do this. I just want to focus on the mass, so I will put a factor 0 on the mass, and I will select all the members that are underground. That one. Okay, now I have a label that tells me that we have property modifiers associated to these elements underground, and I say that associated to that property modifier there is a mass factor equal to 0. So I remove the mass of these elements. And if now I go to calculate the new model, let's see what it will happen in terms of effect on the mobilized mass in the x, y directions. So computing again, this time with the applied property modifiers. Okay, go to see the calculation protocol, update, and as you can see now that I removed the mass that is associated to the elements that cannot move because are under the ground level. I'm almost at 90% for X, Y, and Z. In fact, I'm much above for Y direction and Z. I'm just a little slightly below 90% with respect to the X direction. I can just fix this by computing some modes more. So we go in advanced solver setting and I ask, let's say, for 20 modes, compute, and this should normally fix everything. Okay, calculation protocol. I'm 96% in direction X, 98 in direction Y. I'm okay to perform seismic analysis on this model now. So as you can see, if we can do a small recap, model analysis is the core of the dynamic analysis in SCIA Engineer. With that you can extract vibration mode and vibration frequency. And after you have two tools, one is the IRS method that can serve you to quickly remove the local modes, local vibration mode in order to reach faster the meaningful moving mass of the structure. And sometimes, and it's really common, you have some mass that for some reason cannot move because it's constrained by some support, because it's underground or other reason. And in that case, you can play with property modifiers in order to remove from the calculation that mass, and so to reach the 90% of modal mass required by the Eurocode. Okay, say this, let's go to the next step. So let's move to the PowerPoint. Next topic we want to look at is the response spectrum method for seismic analysis. What is that? It's, as the most of you probably know, it's a method of seismic analysis that can be applied to each kind of building, or doesn't need, there are not restrictions in terms of shape and regularity in elevation as they can be, for instance, for equivalent lateral force method. The only requirement that is needed in order to apply this method, as already we mentioned some minutes ago, is that the response of all vibration mode contributing significantly to the overall response must be considered. What means this in practice is the sum of the effective modal mass for the modes taken into account should represent at least 90% of the total mass of the structure. Put otherwise, we can say that all modes with effective modal masses greater than 5% of the total mass should be considered. They are quite equivalent, let's say, description. So, how to enable response spectrum method for seismic analysis in SCIA? Let's go back to the software to see it directly. We take, as usual, the model that I prepared, and we go to apply, let's say, to enable response spectrum analysis. First of all, let's assure that the functionality is selected into the project settings. So under dynamic, seismic spectral analysis is enabled. Okay. So what should I do now? It's just go to the load cases and create a load cases for the seismic response spectrum analysis. So I can do new. I can call AX the earthquake in X direction, variable load, dynamic, and it's a seismic load case. Here I already set something before, but I can explain you quickly. Where I set a response spectrum. You have the possibility to give response spectrum the through the menu that you have here under Seismic Spectrum tab. We can apply eventually the direction of this earthquake. By default, you see I put it in direction X because this is my load case in the X direction. I can select the other direction, Y, Z, generally, if I want to specify by myself a specific direction that is not coincident with the main axis, but also I can give a rotation of this earthquake with respect to the axis X, just giving some an angle in degrees. I didn't enable equivalent lateral force method. If I want, I can also apply accidental eccentricity in order to take into account by, let's say, masses that is not perfectly as it is in the plan of the building, but in the construction maybe there can be some eccentricity that of the mass due to some mistake or something like that. It can be taken into account. There are several methods to apply this. It goes a bit over the scope of this quick webinar to go into the detail of that one, but briefly after I can choose which is my method of superposition that I want to use. We have three options: SRSS, max, and CQC. I will use CQC. I can specify a damping 5%. It's okay. And after I have option in order to filter the mass that I want to use. For instance, this can be disabled. If I disable that, it means that all the modes that I have computed through model analysis will be used for the seismic analysis. But I can use this filter in order to say, okay, I want to have filter on the total mass ratio. This filter I can set to 80 or 90 or whatever number between 0 and 100%, and it means that if I set 90, it will use all the modes necessary to arrive to 90%, and after it will stop. It will not take into account in the superposition for other modes. I can also put a filter on minimal mass ratio. That filter can, for instance, specify, okay, I want to consider exclusively the modes that mobilize at least 5% of the modal mass. These two filters can be used together, or I can use only one of that. And in case I want, I can also ask for using the residual mode. What means that it's a pseudo mode that it's used in order to reach let's say 100% of the modal mass when there is mass linked to a rigid body motion. Also, other option that I can use is to use dominant mode for the signature of the results. This is a very important concept that I will explain you in a second. I always advise to enable this feature. Now, since SCIA 24, there is an automatic detection of the predominant mode, so there is not any more need for the user to go to manually select which is the mode that should be chosen for the particular direction. So just enable the feature and click on automatic. So I did this for earthquake in X direction. I can just do copy paste and I will rename it in a Y in order to apply the same horizontal earthquake in Y direction. I will not put anything in vertical direction, and that's all. I can just close and I go to compute the linear analysis this time. You see, because it's a linear response spectrum method, it's a linear method. I have two seismic load cases are highlighted here, and I click on calculate. And now, of course, it's performing also modal analysis because it needs it in order to compute the superposition for the response spectrum analysis. And once the model will be done, the two seismic load cases will be computed. Okay, perfect. computation finished. Let me just disable these labels here. Okay. And now I have results as for all load cases, also for the seismic load cases that I can visualize in terms of deformation, internal forces, stress, displacement, checks for steel, for concrete design, and so on. I have full access of all these results. You can see, for instance, for the deformation, I just select the earthquake in X direction, wireframe to go fast. Of course, I have to select something, all, and I will have the results also for the seismic load case, as you can see here for direction X. You can also see, as we mentioned before, that the part underground practically doesn't move. Yeah? The mass that is immobilized here, you see this is the ground level, it's in blue, it doesn't move, so it cannot enter into the count of the moving mass. So now let's go back to the PowerPoint, because I want to have a look at what I was telling before concerning the sign of results. As you maybe know, the modal superposition method that is at the base of the response spectrum analysis is a method in which the response of several vibration modes is put together in order to assemble the final response of the structure. Now, in the superposition formulas, if you know them, they have all the same shapes. They are square root of terms that are elevated to the square. What it implies? It implies that all the results of that formula are positive, always. It means that if you don't do anything in post-processing, you will have all results that are positive, like reaction, all positive internal force, or positive. You will not have a distinction between tension, compression, or reaction of compression and tension, and so on, because everything has positive sign. And for this reason, it is used to sign the results of response spectrum analysis through the use of the predominant mode. What it means? It means that the modal superposition will generate the absolute value of the quantity that we are computing. That value are correct. But in order to assign the sign, we will assign that based on the shape of the dominant vibration modes. That is something characteristic of each direction of excitation. So I will have a predominant mode for direction X, for direction Y, and for each direction of excitation. And at the end, the final results will be just the absolute value, the superposition, and the sign of the predominant mode. Here, just an example of what it means sign and not sign the results of earthquake analysis through response spectrum method. If I do not sign, as I was saying before, I will have all the reaction at the base, for instance the vertical one, that are positive, and that is totally nonsense because I will have an imbalance. There is not equilibrium anymore. If I sign with respect to the dominant mode, I will find equilibrium, so I will have part of the reaction that are positive, part that are negative, and the sum of that will be zero if I do not have any action in the load cases of the earthquake that is direct toward the vertical axis. And yeah, so pay attention to this characteristic, and never forget to sign the results of the seismic load case. As I showed before, it's really something simple. Just you have to enable the case use dominant mode. Okay, so said this, let's just go back to the PowerPoint and have a look at the last topic I want to quickly introduce to you. It's the usage of story results and integration member. That can be two very nice features useful for the exploitation of results of seismic analysis, and not only. You can use these tools for each kind of analysis you can perform with SCIA Engineer. Let's go back to the SCIA model in order to have a look at that. Okay, so story results. There are two types of story results available in SCIA. There is summary story results and detailed story results. Quickly, The summary story results are kind of results for model analysis and that can give you some detail about the data that it's used in the model. For instance, in this computation we use the IRS, and here if I click on the refresh, you can see we can have the masses that are used for each reduced mode of the IRS, that is the total mass of the story and the location of it. We can have some more detailed results through the preview. You see the mass of each story, the position of the center of gravity, and so on, and the inertia that it's used in the stick model, that it's used in the background. What concern instead detailed story results is something really powerful, and again that it can be used for each kind of load case, not only for seismic load case. You can have, let's say, the computation of all the load that acts in a particular element of one story or in a whole particular story, and so on. For instance, let's say I'm interested in results. I can ask for all the story, but I can ask also for some single story. I'm interested in story 1, for instance. No, let's say story 5. And I want to have the results for load case self-weight, so no earthquake results. I want is fx refresh, and I will have for that particular story, so the story 5, the force that transitate in all the elements of this story. You see, each one of the elements of the story has its own resulting force. I can have per member, but I can have also per story. So if I click per story, this is in this case, I should check the FZ. This is the vertical force that transitate in this story due to the self-weight. If I want to have that for earthquake, I can have, of course, in that case will be the Fx, and I will have for that, and I will have in that case the force that for earthquake X load case acts on this story. So in all the elements that belong to this story, and I can ask the same for all the story at once, and I will have the results for all the story. And again, I can ask for all the member or for a selection member the resulting force or the internal force. I can also ask for a kind of selection and so on at a different section level. For instance, I ask it at the middle now, but I can ask at the bottom of the floor in the same way. So it's really something that can be very useful when I want to extract some value that I want to use, for instance, for some kind of post-processing to compare with and calculation and so on. It's always useful to have an idea of the forces that transitate in each one of the stories, mostly when we do seismic analysis. So this is a nice tool that you can use. And another one that it's also a general tool but can be used also for seismic analysis is the integration member. Integration member is something that it can be used to integrate the stresses on a surface element in order to have results in terms of theory of beam. For instance, I can do this with respect to the vertical central core of concrete that I have in this building. Let me just clean the model in order to isolate this part. Will be much more straightforward to understand. I select the core and I hide all the rest of the structure. Okay, I just have the grid and the core. Now I go to create an integration member. Can have several shapes. I can choose the rectangle one. They go from the bottom to the top. Okay, this is my volume of integration. Of course, I need to cover the elements that I want to cover, so I will increase the size of the elements. Okay, it was not that direction. Right, 5 meters. Okay, let's do 6.5. Okay, bottom 2. No, 0.5. And I will do 7. Okay, now I have this volume of integration. As you can see, this volume englobes all the walls that constitute the core of the building. I can ask for this plate element internal force, but I will have a color map that is of difficult interpretation. Instead, through the integration member, I can just go in results for 1D member and say, okay, I want to results, for instance, with respect to X applied load case, earthquake load case. I switch on the integration strip member functionality. I select it in order to say, okay, I want the result only on that. And I say, okay, for this one, I want the MY results. Just let me increase the number of sections into the member. And I have asked for the result. As you can see, we have here results that are really quickly understandable. This is the bending moment. I can have the same for the shear forces, for the vertical forces, and so on. Exactly like it was only one beam, but instead it's not one beam. It's a core constituted by more plate elements. So this is a tool that can be very useful, and I advise to use it when you can. Perfect. Let's go back on the PowerPoint because we are at the end of this webinar. I thank you for your attendance, and I see there is some questions that have been asked. I will reply to them by email after the webinar, the time at our disposal being finished. Thank you again for your attendance, and have a nice end of afternoon. Bye.